All right, so I think I'm going to get started if everybody is ready. So I'm Ed Simpson. I'm your TA for this course. I'm going to start by going over quiz 2, the Burroughs-Wheeler transformation. So this is like free points that you guys should all get on your final exam. I can tell you, well, the quiz results probably aren't available right now. Only one person got a perfect score, and I would say about 20% of you did the transformation correctly, and I think everyone else has some work to do. So I'm going to go through this step by step because I think Dr. Liu left out a couple of key concepts, and I'm going to give you a way to check your work so that you know that you did it right. So the question from the assignment was this string up top. The first step is to put the $sign at the end of the string. Then you enumerate the rest. So I want you guys to pay attention to the number of strings that you have in this matrix. There's 7, and your new string is 7 bases long. So some people missed the question because they had the wrong number of strings. They didn't find them all. So make sure that you check that you have the number of strings that's equal to the length of the sequence plus 1. After you just write them all out, you put them in alphabetical order, sorted alphabetical order, with the $sign on top. And then the last column is your transformation. So that should be pretty straightforward and pretty quick to do, actually. There were only 2 people that got the backwards transformation correct, which I don't blame you guys for at all because we did not cover that. And it's kind of like an advanced topic for those who are really interested by how this thing works. I'm not sure whether or not you will need to do this on the test, but you should probably still know just in case. So you start with the Burroughs-Wheeler string. And what we know from this string is that all of the letters in it are also the same letters that are in the original sequence. So to get the first column, all you do is sort this string. So $AACCGT is the first column of the Burroughs-Wheeler matrix. So from here, you don't know what the letters are in the center, but you actually don't need to know any of these letters. What you need to do is start either at the beginning or the end of the string. So in this case, I'm starting at the end of the string. The first step is to find the $sign that you normally add, and then you find its index partner, which is the letter that goes next to the $sign. So for the first step, it's a $sign. You repeat this process based on the location of the letter in the second column. So in this case, the $sign was paired with an A, and it's the first A in the Burroughs-Wheeler string. So the next step is to find the first A in the sorted column and find its index partner. You put that G in front of the A to the left. This gives you the first G in the Burroughs-Wheeler string. So you find the first G in the sorted column, and you do the same for the subsequent steps. You'll notice that the last step here that I have on this slide, you find the second A. In step 4, there's a center, so you want to make sure that you get the second A in the sorted list as well. That's why picking the correct order is really important for this. And the final answer is on the right. You can leave the $sign or you can take it off. I'm not going to subtract any points for leaving a $sign. So does anybody have any questions about this? All right. All right, so before I get started, I just kind of need to know how much time to spend on each of these topics. I think a lot of people in this room have a lot of experience with most of this stuff, so I'm not going to go through the classic presentation that you guys have already seen 1,000 times, and hopefully I will add some interesting things you may or may not know about. But just a show of hands, how many people here actually got on and set up their account for Karst, like have a computer today, can do something? So about half. It's not as many as I was expecting. And how many people have ever run a job on the high performance cluster? Okay, also not as many as I was expecting. All right, so the good news is this is not super difficult. It's nothing to be stressed out about. All this stuff is pretty straightforward. These programming languages are designed by humans to be used by humans, so you should be able to understand it. The trick is you just really have to put in a little bit of time to understand how to use Unix, and it's not going to be familiar, but you know, you have Google, so Google's amazing and can do everything. Just a basic background, and the reason why I'm kind of doing this introduction is that it helps to understand how computers are structured and how they process information before you try to interact with them on a high performance level. So the basic idea is that a computer does what you tell it to do, right? You give it a list of things. It does those things in exactly the order that you give it. When you're working with a computer, as you do at home, your software is kind of prepackaged for you to just be easy for us to understand what we're looking for. But actually, it's not great for holding huge amounts of information and sorting through things quickly. And so this is what some of the high-performance systems are designed around. This is why we use high-performance systems. So just to cover all of the things that happen when you want to do something simple, like copying a file, it's actually pretty complex. So you start out with RAM. It's an empty space. You can think of it like a place that holds the list of instructions of things that you're going to do and some of the data that you're going to move around. You send the instructions to your processor, and your processor accesses files on the hard drive and puts them into RAM to move them or manipulate them or do whatever you're going to do. So this is already 2 steps, right, before we start doing anything. And then step 3 is that the processor creates a new file on the hard drive, and step 4 would be moving the file from the RAM to the new hard drive position. So this is all stuff that goes on in your operating system and is orchestrated by the core of your computer without you really having to think about it. But all of these things tend to matter when you're working in the high-performance system, because the hard drives we work with are network drives, so you can access these network drives from basically any high-performance cluster at IUPUI. And you may sometimes encounter errors related to your jobs if you try to access resources that you're not supposed to be accessing. If you put too much stress on this cluster, you know, I've done jobs where I write out output at like 2,000 files per minute, and it's just absurd that a cluster should even be able to do something like that. You can have jobs fail because you basically outperform the hardware itself. So it's important to consider all of these things when you structure your jobs. So I guess the next question is really, what is a supercomputer? You know, it's not just a really big computer. Like any high-performance system today, it's just basically a specific architecture. It's a way that these resources are connected that are essentially shortcuts to make them available to you and to make them easy to manage. Each cluster that we have here is designed for an explicit purpose, so it's important that you guys know what resources they have to offer and how to allocate them the correct way. Many of them won't do what you want them to do, so pick them correctly. And also as a job manager, which you're going to need to interface with, but that's pretty easy to do. So this is always a common question, is, you know, why do we have to use these things? I'm not going to present a slide that like equates the number of hours or the number of lifetimes it would take, because those are, you know, tacky. But the simple fact is the aligners that we use can be memory hogs. To load an entire genome into the RAM, it takes somewhere around 30 gigabytes for like a human genome. And so Dr. Liu presented an aligner already where you don't load a genome into the RAM, but there's many different tools that we are forced to use at different times. So the STAR aligner, which is currently still the most popular RNA sequence aligner, does load the entire genome into RAM, and it's an index, so it's even larger than just the genome. It's also references to positions and shortcuts to where it's going to put the reads. So you wouldn't really be able to do this on your desktop, right, unless your desktop has like 30 gigabytes of RAM, which it won't. So without multiple cores as well, you're limited to aligning one read at a time. So on your desktop, you have one processor. Generally, it's hyper-threaded, and it could be like a Core 2 or a Core 4. My desktop upstairs is a Core 8, and it still sucks. But you can use these clusters to get hundreds of cores on a single job. And it's also pretty simple to use these things. So we have 3 primary clusters that you guys will be working with here at IUPUI. First is CARS. This is a balanced system. It has a lot of compute nodes, a few specialized nodes, and if you have some kind of specialized operation, I wouldn't count on these ever being available. And I'm not going to say that CARS even does a great job at allocating the data nodes to people that need the data nodes, right? It's going to take the first come, first served basis. If you say you need a data node, you may be at the end of a long list. I just ran a job on CARS that took 3 days to start, and a job on Carbonate that took like 5 days to start. So for those of you that are looking at doing your projects after today, I would get your topics settled as quickly as possible and find your data, because you could wait a week just to get the first step done, and there's no guarantee you did the first step right. You need time to be able to check everything in the process to make sure that your tools are working correctly. You want to minimize the time that you just spent sitting around. So the second cluster we have is Carbonate. This one is a more memory-intensive application, 256 gigabytes of RAM per node, and you can get these nodes to work together, actually. So you can have at least 512 and more. Big Red 2 is good for parallel intensive applications. This is the one you'll probably see about in most like IUPUI news releases and things like that. This is just to give you an idea of how powerful these are. Big Red 2 just missed the top 500 supercomputers list in the world. So you're probably thinking like 500 supercomputers. That's a lot that are better than us. But if you factor in that only 2 of those supercomputers are owned by universities, and they're pretty much all dedicated to internet service companies, you'll probably come to realize IUPUI has some of the most powerful computing resources of any university around. And it's a great place to be if you're interested in this kind of thing. So I'm going to talk a little bit more about the structure of the supercomputing environment. So when you want to access or manipulate your data, you're going to come into a login node. So this node has a slightly different, sometimes software, than your compute nodes. I'm not going to go into specifics, but just be aware that if you're doing something on a login node and it works completely, and then you go to run it on a compute node and it doesn't, generally it's not the software that's the issue. Generally it's the way that you fed the information to the compute node. But there are some rare cases where the compute node will actually have different libraries or things like that that could cause an issue. So you may need to get extremely technical when you try to fix these things. CAR specifically has a very low number of login nodes. You can only be logged in for something like 10 minutes at a time, but that's actually based on your local client, not on Karst. It will only allow you to do a process that runs for 20 minutes maximum. So sorting a BAM file, depending on which tool you use, maybe you could do that. Generally, you probably can't. But you can get statistics about your BAM files or things along that nature. That's another thing to consider is what you can do yourself and what you have to do on a compute node. Okay. So each of these compute nodes has access to this network file system that I talked about. There's two main spaces that you can access. You have your home setup, and the numbers have changed over the past couple of years, so I can't even tell you how much is available there. And you have the scratch space, which is where you basically have unlimited data you could run processing on, and then you could take your summary files and keep it on your personal profile, and that's what I would recommend that you do. Scratch space expires within something like 30 or 60 days, so anything that's there would be deleted. And even if you move it and move it back, you have to at least move it to a different location. It's just complicated. So don't expect to put anything there and have it last a long time. So the way that you access these supercomputers is through a terminal, or in this case, I'm showing PuTTY, which is just a SSH client. So if you don't have it, you're going to go to this website and download PuTTY. And then if you're a Mac user, you can just use your own terminal. You don't have to download anything. You just SSH to your space. So that's how you log in. But I want to explain some of the similarities between a Unix system and a Windows or a Mac system, and really what the differences are, what you can do with them. So all computers are kind of based around this framework, right? Even though this is a Unix system that I'm showing here. So you have a hardware core, you have a kernel, which is kind of like a translator, and then you have a shell, which is how you interact with the kernel. And then around this, you could just think of it like all your applications that you install, like Microsoft Word or anything else that you want to do. So your personal space is the shell, and you can change the type of shell. So that would be like, imagine that you're using Windows and you don't really like it and you want to switch to Mac OS or something like that. So you can actually change the shell just that easily in a Unix system. It will change the commands that are available to you. It'll change how some things are processed, maybe your profiles, maybe your colors, but it's essentially a customizable operating system, and it's entirely customizable. So what we have on the right is an example of how you normally run or open a file on a Windows system or a Mac system, right? So you've got this visual representation, you click it, you can double click it, it'll open it, you right click, you go to open with. Well, imagine that every time you use a file or want to look at it on a Unix system, you're just going to open with and then typing the name of the file. So in this case, you would type PowerPoint space the name of the file that you want to open with PowerPoint. It's basically the same thing. The difference is Unix allows you to make your own commands. So they have some built-in commands like this. These are the most common. My personal favorite is man time, because it's just awesome. But you can do a lot of the basic things and string these commands together. So it's extremely powerful to be able to copy files, rename files, sort files, organize files, backup files. You could do this all in a single line. And you could repeat this as a script and just, do it as many times as you want to. You can schedule it happening overnight. You can do all of these things. And generally, they're not as easy to do on Windows or Mac systems, but that's not to say they're impossible. So some things I specifically want to draw your attention to, though. You see Control-Z at the bottom allows you to put something in the background. That's the equivalent of me tabbing out of this, right, and doing something to my slideshow and then coming back. It's suspending whatever you're working on. But if you have something that you want to run, like a script, you could put an ampersand at the end of the line, and it will execute that while you go on to do something else. So that's going to be helpful to work with your time management. So the thing about Unix, too, is that Unix basically is a programming language, right? It has variables, it has commands that you can execute, but it also has another programming language built into the programming language called awk, which is insanely powerful and very difficult to understand. So this is not what I would consider like a human syntactic language. It has a lot of shortcuts and symbols, and it could do practically anything you can imagine, but it is going to take a really long time to get good at. So I wouldn't worry about that. None of you will need most of what I'm showing you. So sed, grep, xargs, these are all ways to string your commands together and get a lot done in a short period of time. Piping gives the output from one command to the next command. Chaining is where you wait for the command to finish successfully before you perform the next command. So if I want to copy a file, for example, and I give it a location and that location doesn't exist, the chain will be broken. You won't end up overwriting stuff or destroying stuff if that's the case. So you can use all of these logics to avoid making mistakes. You can redirect output, you can append output. The only thing Unix basically can't do is teach you how to use Unix, so you have to spend a decent amount of time on your own. For customizing your environment, you really have, just like the sky is the limit kind of options for this. So the first thing I wanted to do here is show you guys how you look at software that's already available on Karst. How can you use a tool that you don't necessarily have to install? Because most of the NGS tools that we use, we've actually requested Karst to host. So the basic stuff is pretty much available already. You don't have to go through a lot of steps to do this. So let me just quickly log in and show you what I'm talking about. So this is the SSH key. The first time you log in, it will ask you to accept it. That's to prevent spoofing. You can read about security stuff later if you're interested. So you notice when I first log in, it gives me this welcome message. It says what my name is, the time, blah, 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 blah. Over here, this is a list of modules that I have loaded. And I have a stupid amount of things on my profile. My profile has been through a lot of iterations, and it's very confusing now. But if I wanted to start from scratch like you guys will be, I could simply delete a configuration file, but I'm not going to do that. So if you want to see what's already available, you can just do module available, right? So these are all of the packages from various laboratories from around IU and IUPUI. You can see that each of these has versions associated with them as well. So if the pipeline that you want to use is specific to a particular version, you can manage that generally with this. You can also manage it by installing it into a particular folder, and then only linking that folder to your profile when you need to use it. So a lot of the NGS tools are going to be in the life sciences section. If you look through here, there's some extremely popular ones like BAMUtil, BCF tools, BED tools. Many of you will probably use SAM tools, right? So over here, there's quite a few versions of SAM tools. SAM tools is a program that allows you to look at a binary file or a BAM file, and what you can do is essentially just take a look at your data as Dr. Liu has shown the file format presented. So normally a BAM file, you won't be able to read it. But with SAM tools, it'll take the binary, convert it to whatever character type that you want. And you can look at it that way. So if I just want to look at like a FASTA file, I do that with Vi. Vi is a text program, just like WordPad or Microsoft Word or any of those other things. There's a lot of different options out there, but I have a specific reason why I use Vi, and that's because it's conducive to programming as well. So here we have some example reads from a FASTQ file, right? And if I'm going to process these programmatically, what I need to know is which characters are there, which characters aren't there. So a lot of times, these files have different ways of encoding something like a space or a tab or a dash or a backslash or things like that. If I need to know what the hidden characters are, I can do set list in Vi, and it will show me the end line characters. if there were tabs, it would show me symbols for those as well. So I'm bringing this up because it's an extremely common problem that students have when they're facing any type of programming data. They go to run something, they get an error about the number of columns or the number of rows, or it just, poops out some random stuff. And you need to be able to check your files to make sure that the lines are what they're supposed to be. But after you're in this, you can use this vi utility to customize your environment, right? So I'm talking about the modules at the moment. So if I want to use SAM tools, since SAM tools is already installed on my profile, normally I can just type SAM tools and it will tell me some interesting things about the utility. Generally you can do like a -H or whatever if you need some help. But if you want to install SAM tools on your profile, you need to be able to see the hidden files. So that way when you log in, you don't have to do this every single time, right? So if I go to bash RC, this is specifically like, I'd say visualization and user shortcuts. And if I want to look at software on Karst that I'm interested in using on a regular basis every time I log in, I go to modules. So if I open up the .modules file, you can see all of the code that I have set up to run my environment. Now, as SAM tools is loaded already, I can just comment it out and unload. But let's see here. Okay, so if I get rid of SAM tools like that and I type it, nothing happens. But if you want to install it yourself, you have to edit that file. And I've specified versions in mine. And now that I've edited the file, though, the changes won't take effect until I log in. So if I try to go to SAM tools, it still won't be there. If you want them to take effect right away, yeah, you have to source it. And it will reopen all of the tools that you have here. So that's a way to get software to show up on your profile every time you log in. And it's also a way to use the built-in stuff from Karst. So if that's a software that's available, chances are you're going to have a lot of stuff that's maybe not so available. I'll talk about that in a minute. But like I said before, with Unix, you can create your own shortcuts and your own basically anything. So let's say that I want to access my scratch space. So I have a terrible memory, and I never really know how to find my scratch space, so I just made a command to do that, so I never have to know where it is. So to make this command, I go into my bash RC file, and here I have something called alias space scratch, and then I just have the change directory command with a string. So if I type scratch, it just takes me to that space. So I suggest that you guys go ahead and make the same command. You can follow the slides because all the things that you need to do to make that are in here already. All right. So those are two basic ways that you can get Unix to do what you want to do. But there's a lot of tools on here that you won't be able to just load from UITS's repository and that no one else is using. And specifically, if you're like our laboratory and you're making your own tools or your project has something to do with writing a new program, you might want to be able to link it to your profile. So I'm not going to go through the steps for how to install these things. Like I said, you can find most of this stuff on Google. But you generally need to download what's called a tar file, which is the same thing as basically a zip file. You can follow the package instructions, but just be aware that you might have to install 4, 5, 6 packages to get this stuff to work. You'll also need to implement programming language environments that are specific to these tools. So if you're using a tool in Python, you might need to install libraries inside of Python, and that can get complicated. But the nice thing is UITS has moved over to something called a virtual environment for some of these programming languages. So if you click this link, it'll show you how to set that up. Basically, a virtual environment is a folder. And all you do is install Python into one folder that gives you access, like admin privilege over that space. So you can install utilities that do everything for you. You don't have to compile everything yourself. And a lot of those instructions are available online. Transferring your data to and from the cluster involves using FTP or SFTP. So you need to get an FTP client. This is FileZilla, which is just part of basically Mozilla or whatever, Firefox nowadays. There's certain areas where you guys will want to get data from that you will not be able to use this. So, for example, the gene expression omnibus requires you to download a GEO tool. And that's because they store their data in a very specific format, and you need to actually split their data. So if you're using NGS data, you'll likely have an R1 file and an R2 file, so that has to do with paired reads. And when you download the data, you can't simply just say, oh, I want to get this project. Generally, you have to split the files inside the project. You'll need to open those files after you're done using some of these text tools to check that they have the reads that they're supposed to have. And you can count the lines in the file. That's a very useful way to make sure that everything's going right. But these clients are also very simple. You connect to them the same way that you connect using a terminal or PuTTY. So about the torque job system. So that's just interfacing with a basic user environment and running things that are less than 20 minutes. But if you want to do some sort of an alignment, or if you want to have a job running in the background, you need to be able to talk to the high-performance cluster. So there's a few types of nodes available on Karst and a few types of queues. I would recommend, because a lot of people aren't aware of this, is using the debug queue to check things or even run something that's less than 30 minutes. There's also what's called an interactive node, which basically no one uses. So I would try to log into that, and maybe if you have anything less than 8 hours to do, just let it run on your computer. But yeah, these are the specifications for what the different queues are. The other things that I want to mention about the torque job system is that the more you use it, the less UITS lets you use it. So you need to know what you're going to do and how to do it before you go into the system. You can test these commands in Unix without having to submit a job. So for example, when I make scripts, if there's a variable that I want to save, I could go so in Unix, I just made a variable, right? And then if I want to see what's in it, I have to hit echo. And I can always try to change to it, but it doesn't exist right now. So it should fail. So that's the general idea, right? You're going to write a script, you're going to have these variables, and you're going to need to make sure that they work before you send any of this stuff to a job system. Okay. So submitting a job is the same thing as anything else in Unix. You just give it the utility that you're using, which in this case is qstat to check the status of your jobs, or qsub to submit a job, or qdel to delete something. I've included this script here, which deletes all of the jobs associated with a particular username, right? So if you use this after you've made a mistake, it'll save everybody a lot of time. The way that the queue system works in Karst is even if you made a mistake, it's going to try to run something, and it can estimate the amount of time that it takes before your job will start. But that's all based on how much time everyone else has requested. So if you have a bunch of jobs that aren't actually going to run, everybody is going to think that their stuff won't start for like 2 weeks, and then hopefully your jobs will fail quickly. But otherwise, you could lock down the cluster for a really long time. So this is what a job script looks like. At the top, you define what shell you're using, which is optional. But then you have the section that Torque looks at to look at the parameters for the job, right? And then you have what the script actually does. You can follow this slide, basically, and make this file with Vi to submit your first job if you're interested. When you run a job, you're going to get log files associated with that particular job. And you're also going to get an email if you define the email fields. So the emails are pretty helpful, but if you have hundreds of jobs running, it gets pretty obnoxious. So sometimes you might want to turn it off. This is a job that started yesterday. It ran for 16 hours, and then it failed because I used over 130 gigabytes of RAM, and the cluster couldn't support that. So it's good for tracking this because this isn't going to end up in a log file on your system, but it could give you an idea of what you did wrong and why something kicked you off of the cluster. Other than that, each cluster has specific parameters that you need to define. So for many of you that are just kind of getting started in this stuff, I wouldn't recommend you use another cluster besides Karst or maybe Carbonate because they're the simplest to use. They have some very advanced features on Big Red 2, and they can be very difficult to use correctly. So the next thing is basically debugging your stuff, right? So before you run anything, you want to double, triple, quadruple check all of this over and over again. You can test calls using your own terminal. So like samtools space whatever, if you're trying to cut reads from a particular file and print the output to your terminal. So that way you save some time. This can also help you make sure that the files are going where you expect them to go. Okay, so that's mostly what I have for Torque and for the Unix systems here. But like I said, you really have to use it, and anything I show you is kind of going to be a waste of time today because you're not going to remember it anyway. But I'm going to stay here for the rest of the time anyway afterwards, so if you guys want to set up your environment or test something out, you can do that, and I'll help you figure it out. Yunlong, I contacted him last week, and I was asking if I could get you guys some extra credit for running a job, so I think you're aware he's currently in China, and he hasn't replied back to me yet. So as soon as I find out if I can get you guys some extra credit points, hopefully someone will tell you that's going to happen. So anyway, this is more the traditional way for how we process NGS data, but there's a couple of new techniques that are going to get really popular, and if anyone here is going to go into bioinformatics, you're going to maybe have a completely different paradigm for working with this stuff than we do now. So a lot of people have heard about cloud computing, and essentially there's not a great description for what cloud computing is in the general public, but basically cloud computing is just a bunch of computers. So the framework for cloud computing is based on 2 papers released by Google because they were very generous, distributed file system and the MapReduce framework. So if you're interested in any of this cloud computing stuff, I suggest you look these up. But The cloud computing that most people are familiar with is simply just storing files in a redundant and safe manner so that they're always accessible and secure. And while you can run some things with the traditional cloud network like this, or like everyone seems to access nowadays, it really doesn't give you that much of an advantage because, like I said, these high-performance clusters are specifically designed for this kind of thing, which means the processors are more powerful, they have more RAM, and there's just simply certain things that you can't do without those resources. But what is coming up is on-demand computing, which is basically Amazon Web Services. So we have a new partner here at IUPUI, and they work with protected health data. And they offer sort of an interface to Amazon Web Services, but Amazon Web Services is kind of like the supercomputing cluster for the world right now. And a lot of people are moving their data over to Amazon Web Services. A big reason for this is that you only pay for the amount of computing power that you need and while it's running. And you can basically get any configuration you want to because you define the operating system and all of these other things. They just spin up as you need them, and they can talk to each other. So the system that we have here is by a company, LifeOmic, which will be giving you a presentation later this semester. But their framework is based on Amazon Web Services, and it uses Docker containers. So a Docker container is a zip file, it's a tar file that has individual pieces of software wrapped inside of it. And you run a Docker container like you run a command or open a file on any other machine. You just say, run my container, or you give it an argument. The reason why this is a topic even in this presentation, or why this is sort of up and coming, is that all of the versions inside that container are locked. And we spend sometimes weeks just installing these tools to get them to work. With Docker containers, you don't really have to install anything, right? Someone's already built the container for you, so you just open up Docker with that container and it does what you need it to do. The other cool thing is that it packages as many steps as you want to in a single command. So you can run an entire NGS pipeline with one command. And that can also define the resources and automatically detect and configure how many processors and components you need to do this kind of stuff. So the good news is it's going to get easier. But for the moment, you probably still need to use the HPC cluster and some modules to at least do some basic analysis. But short of that, I really cannot prepare you guys to use a high-performance cluster. So if anybody wants to stick around and has questions and wants me to help them set up an environment, I can do that. Does anybody have any questions about anything I presented today? Or yeah, go ahead.
So when you schedule a job,
yeah,
does it also go into the shortcuts that we created and also the .module file?
It does, yeah. So what a job does is it's just a simple text file that tells Unix what you want to happen. And when it runs that text file, it loads your profile as you define on the login node. So that includes all of the software that you loaded with .modules and everything else. So if you want to be sure that a tool is available to the compute node, all you have to do is make sure that it's working on your personal node when you log in, and everything should run smoothly. It will also have access to your personalized commands, anything else that you normally use when you log into the system, it should be able to do. Any other questions? No? All right.